Let's just get started. Hello everyone. Welcome to this problem solving session. Uh, we will be. I will be. Discussing this week content. I will summarize first. For few minutes, I will summarize the content covered in this last week, and then we will solve some problems related to previous years and yeah. This week content was mainly primarily on MOSCAP. We will be discussing the MOSCAP in this uh, in this session. Let me just get started. Basically, like the MOSCAP in different regions of operations and the how we drive the threshold voltage. Basically, MOSCAP is the fundamental building block of the all the CMOS, MOS, NMOS, all the devices. The MOSCAP is the fundamental to define the turn on and threshold characteristics. So basically, what happens, like how to turn on the transistors, all that dynamics and those things are deal with the MOSCAP. So if this is the N plus, and if this is the gate oxide region, and if this is the metal region, then basically what is, if you take cross section of this, then it basically forms the MOSFET actually. So if you applied substrate to gate bias, then like the some like such some rearrangement of charge happens, and that is basically you deal with the MOSFET, and it is different compared to normal PN junction and the whatever happens in BJT. That is so it is bit different from that. So in the last class, basically we discussed, or even in this course, we primarily discussed what are the ideal MOSCAP, what are the characteristics, and we will drive some expression based on that. Let me draw the structure of the MOSCAP, and this is just uh, this is if you consider this as a metal, and this if you consider that's a oxide. So and this is the semiconductor. So metal oxide semiconductor. So this is the junction, and this cross section if you want to see in the actual device. And if you take out the cut in this MOSFET, and this is the cross sectional view of MOSFET, and if you take cut along this, then you will reach this region as a MOSFET. So basically, if your like last class, if we discussed, if your substrate is P type, so basically that the carrier inversion layer is N type, and then that you will call as a NMOS. NMOS. Similarly, same is there for MOSFET. So basically, if your substrate is P type, then your the channel region is NMOS. So this we are talking about the enhancement type of devices, which require like certain voltage to be applied to turn on the devices. So that is this, and then like we can draw the band diagram. So basically, what has happened is so we can draw the band diagram across this. So if we take the cross section along this, then we can draw the band diagram, and then if we draw the band diagram across this cross section, so then we encounter three different regions. The first region is metal, which is the metal. You need to draw the Fermi diagram, and then that is the oxide, and it is a different material compared to the silicon, and it is a dielectric material, so it will have larger band gap compared to the silicon. So while drawing the band diagram, basically, so equilibrium band diagram you can draw, and you basically draw the constant Fermi level EF. So let me draw. So if you want to draw the band diagram, so basically you draw the first constant Fermi level EF, and then basically you draw the different band offset in each of the. So this this is the PMOS, because this is the P type substrate. In case of NMOS this is, and this is P type for NMOS, this is P type substrate. So that basically you need to draw the conduction, the valence band closer to the Fermi level. So you will draw like this, and then so basically, and similarly you can draw the valence band here, conduction band here. So in the oxide basically is, it's a dissimilar material and it has a higher band gap, so it will have a band offset like this. Similarly here also it will have a band offset like this. And in the metal, because like the concept of band does not exist, because that follows the the normal normal Fermi statistics, and you can define the characteristic just by drawing the Fermi level. So this is the band diagram. So so depending on, now this is that the zero bias. So zero bias, ideal MOS. So, what is the ideal MOS? Basically, you consider the metal work function as the semiconductor work function. First thing. Second thing, you uh, consider the dielectric region, this oxide region or dielectric region. Dielectric region is free of any charge carrier. Uh, so dielectric region is free of any type of charge carrier. So this is this, and no interface charge, no interface trap is there, no no Fermi level pinning, and these are bit higher level concept. And this we can just take it simplify at this like first level course, which is this. So basically, now this we can operate, we can apply a gate bias, and gate bias in different region. So we can apply a gate bias VG, which is smaller than less than. So we apply a bias. So here to here we apply a bias. From with respect to substrate, we apply a bias. So we can apply a that is the known as the bias. So we can apply the gate bias. VG is greater than 0, VG is 0, and VG is less than 0. So we will consider the case, each of the case for. So what happened is, so since the EC is basically minus QV, B by V by Q. No, no, yeah, no, yeah. So EC is minus QV, and that potential, or you can write V is equals to the so EC by Q, or you can define that like the EC is basically energy, and potential you define as a with respect to unit Coulomb charge. So you need to divide by Coulomb charges, and that you can define in volt. So basically, when you apply a gate voltage, so basically what it does is it does pull level up or down. So basically, if you apply a positive bias, then this EG will be negative. So this will move down for positive bias, and this will move up for negative bias. So, depending on the biasing condition which we apply, there are two different kind of regions are there. So, two, not three different regions are there. So, one is the accumulation, and other is the depletion, and other is the inversion. So what happens is when you apply a positive gate bias, so what will happen is this band at this side will become lower, uh, this lowering of this band is minus Q time Vg, and that this band will pull this in the oxide region. There will be field exist, and if there is a field, then there is a banding of the band. So then it will be this slope. The band will become like this, and similarly here also, like the that gate voltage partial of that will appear uh, uh, so this is for positive gate voltage. So let's consider first as a negative gate voltage. uh, Negative one. So first let's consider a negative case. So if you apply a negative gate bias, what will happen is this band will move go up, and similarly this will go up, and this will go up, and also this will go up. No, not this. So this will this will go up, and it will be like this. So what will happen if you apply a negative gate bias? So the field will be in this direction. So from substrate to this side. So this has the like larger number of holes are there, larger number because this is a p-type carrier. So these holes will start moving in this direction, and then they will accumulate at the interface. So basically what will happen is like at the interface your semiconductor will become more p-type. So like the Fermi level the at the interface Fermi level will move closer to the uh, closer to the valence band, and that basically it will follow this kind of band bending. So there the band bending will be like this, and you can write this ei level also will go like this. So this region is known as the accumulation. And what happens is like this so the charge density rho x is basically proportional to some constant times exponential of minus bg by kt by q. So this see like that charge density is basically increasing exponential with respect to the potential drop across, or you can write the surface potential. So the surface potential is the potential which is dropped across the semiconductor region. And as you can see, like as you can apply the negative bias, this will go if you increase the surface potential, the charge will go exponentially high. So if, so this will be proportional to even na, what is the equilibrium number of whole concentration is there. And then that there will be like this is in the if you plot the charge density, then here will be huge pile of a charge will be there. So if you plot in the linear scale, then there will be a sheet of charge here, or the log scale it will look like this exponentially increasing uh, a sheet of charge. So this is known as the accumulation. And all the charge basically on the other side of the dielectric interface, basically there will be a negative charge buildup will be there. So as you can see, this is minus q and this is q. And if you know from the 12th class physics, if some dielectric material is separated, let's say epsilon ox, in between two charge plate is um, two sheet charges, if you are separated by some dielectric material, then it forms the parallel plate capacitor. So the capacitance is given as the this capacitance is given as the depletion accumulation capacitance, and which is equals to epsilon naught a by d, epsilon naught a by t ox. Basically that t ox is the thickness of the your dielectric region, and you will get this uh, this expression. So the capacitance will be in similar to the parallel belt capacitor. Even you can do more detailed analysis, but that is not important for the basic course like this. So now, like in the negative bias, the accumulation happens, but uh, so uh, so so uh, let's analyze this. Now what will happen is when you apply a negative gate bias. So uh, so let's say let's draw the equilibrium band diagram. This is EF, and this is EV, and this is EC, and this is oxide region. This is oxide region, and uh, this is the metal region. So now if you apply a negative gate voltage, that this side band will be pulled by minus Q times dG, and some of this voltage will appear across V aux, and other will appear across V psi, and that so basically what will happen is this, because of this application of this voltage, this band will pull down, and similarly this band will also will pull down, and that you can draw like this, and that you can draw like this. So in the bulk, the equilibrium condition prevails, and in the this region basically, uh, this region basically your this is your psi f basically. So this basically you, as you can see like this, this conduction band is moving closer to the Fermi level. So the substrate at the substrate at the interface is becoming more n type. So for n type, so the accumulation of electron will happen here. But since this is a p type substrate, so since this is a p type substrate, the electron will accumulate here. So since this is a p type substrate, there is a very less number of electrons are there. So what will happen is these electron will come out by depleting the substrate actually. So that is known. That's why this is known as the depletion region, and you can like you can draw the charge pictures actually. So if you draw the charge pictures, so what will happen is like this, because of this because the electron has moved out of towards the interface. Whatever remaining side is the depleted holes or a depleted substrate, and that because the doping concentration is constant, and that, or you can say depleting means like the hole will so the electron should increase so that the hole should move down, and that means like your holes are pulled away from the junction, and this substrate is getting depleted actually. So that is known as the depletion region, and the charge density, if you plot, that is given by uh, uh, minus q n d. So it is not like this. So the charge density is given as minus q n n a by epsilon, and no, this is plus, no, yeah. So this is q and minus q and a by epsilon. So this is charge density at x, and at the interface basically, and this charge will appear at the this interface basically uh, will have your positive charge actually. So uh, that will make and the at the interface there will be negative electron will get accumulated at the interface, but their concentration will be similar to the positive charge here. So that is the depletion region. And if you apply such a bias that this basically at this interface, your substrate become from p type to n type. So what is mean by becoming n type is basically your Fermi level will become closer to the conduction band, such that the electrons electrons accumulated at the interface n is equals to the p. Doping concentration is the in the substrate, and uh, so then it will be basically inverted, and then this band bending will be, in that case this band bending will be such that this this bending is 2 phi f compared to the 0 y scale. So this banding is 2 phi f for inversion to occur, and as you apply more bias, then this band bending will further, and the charge will get increased. So at the at the threshold, your surface potential of silicon it will be equal to 2 times phi f, and like the gate voltage you can calculate by Vg equals to V oxide plus V silicon, and this V oxide plus VSI you will calculate is V oxide plus 2 times psi f, and psi f you can calculate what is a function of substrate doping density and those functions, and uh, uh, oxide voltage you can calculate just by applying the boundary condition at this interface. So that is the this is and as you apply more higher and higher bias, this interface become more and more n type, and you can see like you can say like that more inversion is happening, and that the channel has been inverted. So that is the concept, and that is the summary of this week. And this threshold voltage is defined as where the surface potential psi of S is equals to 2 times psi f, and that if you know this surface potential, then you can calculate how much exact gate voltage you need to apply to create this kind of surface potential, and that will be a function of thickness of this oxide region. If you have larger oxide, you need to apply higher voltage. If you have the smaller oxide, you need to apply a smaller voltage. So that was the summary of this week content. So we will start the session. We'll solve some problem related to this week content on MOSCAF. So let's just start those problems. So the first problem talks about the charge configuration of the ideal MOSCAF for an applied gate voltage VG is given below. Answer the question that follows. Note that the free carriers are represented in red and blue, and where is the bound charges and represented in magenta color. I don't know where is the magenta color. The type of substrate and the biasing condition of the MOSFET is. So basically, what is happening is your so this the interface charge is negative. So this is negative. So and that basically so and this so this so and the substrate there is no charge is given. So that means that like this substrate depletion is not happening, or very a very thin layer of depletion or just majority charge accumulated. So this negative charge are piled up. So means that means this is n-type substrate, because the negative charge are electrons, and that means this is n-type substrate, and that this region is accumulation basically, which because this charge is appearing just at the boundary of the oxide layer, and that means this is a n-type substrate, and the region is accumulation. So the accumulation is because this the surface charge density in the away from the junction is zero. So we can say like the whatever the surface charge coming at the interface is coming because of the accumulation of the majority charge carrier at the interface. So this is the correct answer is n type depletion. This is wrong. P type depletion. This is wrong. N type accumulation. This is the correct answer. And P type accumulation. This is wrong. This is also wrong. So that is the correct answer. So let's move to next problem. So if you have any doubt, then I will pause for some time, and if you don't have any doubt, then we'll start next problem. Okay, so let's start next problem. Uh, the field profile resulting from the above charge configuration and the corresponding band diagram is given by so basically field profile we need to consider like which field profile. So band diagram. So this is n type basically. Substrate is n type. So if we draw the so bias is negative. So negative bias and the so so n type accumulation. So yeah. So that so basically the bias is negative and the substrate is n type. So if we draw the zero bias band diagram, then we will draw the EF as constant. Then these two boundaries, one is this is the metal oxide semiconductor, and if we draw the band diagram, so here we will draw this is since n type, so we will draw the Fermi level closer to n level. Conduction band and the valence band will be here. Similarly, oxide level we can draw like this, and oxide level here we can draw it like this. So this is the band diagram. So now if we apply the negative bias, so what will happen is so basically so if we apply the so so if we apply the bias, this accumulation region. So for n type substrate for accumulation, you need to put band down. So basically, so for n type substrate, so to have the accumulation of the majority charge carrier, this band at the interface will become more n type. So this bending will be downward, and correspondingly you can write this as a you need to apply a gate bias and negative gate bias, and that will be like this. So this you need to apply negative QVG. So the QVG is negative. So that and that basically is the accumulation region actually. So the charge profile in this will be uh, will be so the so the band diagram. So this for n type substrate, this is the depletion band diagram. For n type substrate, this is the depletion band diagram. Because see, at the interface, your EC minus EF is increasing actually. So it is becoming more E type. So it is the depletion case. But in the one case, the interface is getting more n type because EC is moving towards EF, so it is becoming N type, and so that is there are huge number of electrons are there, so they will move towards the interface, and they will form the inversion layer. So basically, all the in this case because the in the semiconductor because this we have a huge pile of carriers are available in the substrate, so they will we need to deplete a very small amount of uh, small amount of semiconductors are needed to produce the charge which we need actually. So basically this if you consider a typical doping concentration, this doping concentration is 10 power 17 to 10 power 18 per centimeter cube. So 10 to power 17 electrons per centimeter cubes are roughly available. So you need very small depletion bit in the semiconductor region to accumulate the amount of charges we need to put at that. So basically, that we can assume that all the field will be appearing across the oxide region only. There will be no field across the metal or semiconductor region because like this because we will have very shallow depletion which provide the adequate number of charges. So depending on this concept, actually, the correct option will be so this the field in the oxide will be there, and field in the silicon won't be there because there is no depletion. So basically, if you apply the Gauss law, field will only exist if you have non-negative, non-zero charge density in the substrate. But if you can assume that the substrate is quasi-neutral or neutral, then you can assume charge density at zero. Then basically you can assume the field as zero or constant, because other side field is zero, so that this side also field will be zero or constant. So that the with the given option, the correct option will be B and one. So the correct option is second one, which is B option, and first band diagram is correct. So if there is any doubt with in the problem, then you can ask, or otherwise I will move to next problem. So let's move to next problem. So yeah, so let's move to next problem. So a student experiment with the above MOSFET by applying a different gate bias. The band diagram for the same is shown below. Note that the EF equals to EI at the SiO2 interface. So EF equals to EI has there at the interface. Also, the free carriers present are represented in red and blue, where the bound charge is represented in magenta color. Assume Kt by Q equals to 1025 milli electron volt, and Ni is at 10 power 10 per centimeter cube, and the other typical parameters are given. So the MOSFET is biased in which region? So basically, so let's find out in the bulk away from the junction. EF is most closer to the conduction band, so this is N type substrate. And this, now at the interface, you see like the EF is this, so EF is this, and EC is this. So the EC minus EF at the interface, so this is EC, this is EF. So EC minus EF at interface is larger than EC minus EF in bulk. So EC minus EF in bulk, EC minus EF in bulk is smaller. So this is larger compared to EC minus EF in the bulk. So basically, the at the interface, this is becoming less N type. So it is becoming less N type. So this is means that the electrons will be pulled out of the interface region. So that means we can say like that the substrate near the interface is getting depleted actually. So that means we can say, and this the so basically EIN minus EF is basically your surface potential, and we can say it is in the depletion region or inversion region by telling this how much this interface has been depleted. So they have said that it has been equals to the interface. So this is the just the threshold of the inversion layer region, because this now the interface will become intrinsic, because now EI will be EF is become nearly equals to EI. So this has become like the depletion is such that the interface has become completely depleted, and it has become like the intrinsic semiconductor. So that we can say like this is operating. So this the psi f is uh, equals to phi f, but less than equals to 2 phi f. So this is still away from the threshold region or inversion region, but is equals to the surface potential. So that we can say like this is the semiconductor is in the depletion region actually. So the correct answer is the depletion. Accumulation is wrong, inversion is wrong, deep depletion. So deep depletion, we will see that deep depletion later if time permit. So deep depletion is basically like if you apply the gate voltage, if you sweep very fast, so then what will happen is that this minority carrier generator generation, they in practical devices they generated by like thermal like the uh, thermal excitation of those charge carriers, and which is very slow process. So you can say like it will take time. So basically deep depletion, it's like the interface will become more and more depleted at beyond threshold. So that for basic codes it's not that much important. So that the correct answer is the depletion, and the flat band is not the case because this is ideal case. The flat band condition is there when the band is like EC and EF are just constant over the throughout the substrate. So this is the third problem. So now let's move to next problem. So this So the same problem, the charge configuration that represent the MOSFET biasing as shown in figure. So basically in this figure, because we have concluded the depletion. So in the depletion region, uh, uh, there will be there will be pile up of minority carriers of at the interface, and there will be so this pile up will happen because by removing the majority charge carrier from this region, so they will leave a immobile ions back, so that this will be depleted of majority charge carrier, so there will be a depletion charge. So then, basically, so what will happen is this is becoming more p type. So the accumulation carrier will be positive. So because the hole will get accumulated at the interface, so charge will be positive, and the substrate charge will be negative. So basically, you can write the correct option will be in the depletion actually. So you will see like this no no for n type of carrier the substrate charge will be, because ions are positively charged, so the substrate charge will be positive, and very small negative charge will build up on the interface. So this interface will have negative charge because this is a positive, and somehow you need to balance the charge because the current you did not still has not flown. So you need to balance this charge, and this will appear on other side of gate voltage, and which will that this charge will get transferred by the applied gate bias or battery. So the correct answer will be C part, which is the depletion of the substrate and the accumulation of negative charge at the gate metal interface will be there. So that is the this is wrong. This is also wrong because the positive charge shown at the interface is very large compared to the negative charge which has been depleted. That is not the case. So this is wrong option in that sense. And this in this actually the charge density or depletion charge is shown as negative. So this is also one of the wrong answer in that sense. So this let's so now the field profile for the applied bias case in the figure is so basically this is the oxide region. If we draw the charge picture, so this is the charge picture q n d by epsilon. So this is rho, and this in the oxide region we can assume that zero charge, and in the metal you can assume there is no charge. So then basically, if we want to draw the field, so basically if we start integrating from field from this direction, so this if we apply the proper boundary condition, so here the field will be zero where the neutral region prevails, and here the field will linearly increase because if you integrate this charge, so basically, so this is dE by dx is if you apply the Gauss law, then dE by dx is basically q and d by epsilon, and if you integrate, you will get this q and d x by epsilon plus c, and at x equals to x dip w dip depletion bit, the field will be zero, so this will become c equals to minus q n d by epsilon w d minus, and this will be electric field will become q n d by epsilon x minus w d times. So this, as you can see, like this is the negative field because x is, so this is a WD, and because x is less than WD, so this number will be negative, and this field will be in the negative direction, and it will linearly increase with this slope actually. So now in the, now you reach up to here, and now if you say like if you move in the this oxide region, because this is in the free of interface trap charges that there, so this dE by dx at oxide region will be zero, so you can say E is constant, and that constant basically you apply a boundary condition, like this is oxide, so you apply a boundary condition, electromagnetic boundary condition, as d1 equals to d2 or d1 minus d2 equals to rho surface charge density, and then if you apply this, so then it will epsilon ox, so this will be epsilon ox e ox equals to epsilon si esi at the interface. So basically epsilon ox you can draw from epsilon si by epsilon ox times E of Si at the interface. So from the interface field value, you can draw this, and this you will see a sudden jump in the field, and you will see the band diagram like this. So this the correct no, this is positive actually. So this will be QND plus positive. I think this is positive. Yeah, yeah, this is positive actually. This will become, because this charge is positive, so this field will look like this. No, yeah, this is correct actually. Just wait. Yeah, this is correct actually. So this correct answer will be C option, I feel. So the correct answer will be C option. uh, so yeah, so this will be the correct option. uh, so so the field inside the oxide region is at the, compared to the field in the oxide region is compared to the silicon what is there. So basically this boundary condition you need to apply, that oxide region uh, epsilon is given, basically oxide region epsilon is uh, uh, 3.9 and 12.11.8, so you need to apply this condition. So basically epsilon ox E ox equals to epsilon Si ESI. So basically epsilon ox is given as 3.9 epsilon E ox, and this is 11.8 E of Si, and this E ox by 11.8 times 3.9 and ESI. So this you approximately you will reach around 3 times E of SI. So the correct answer will be this first one, 3 times the ESI. So this ESI is basically field at the interface and the air oxide field, and this will be constant. So this is flat in the oxide region. So the doping concentration in the semiconductor and the electron concentration are in the electron concentration at the SiSiO2 interface is given by this. So basically, so this you can calculate. So this so EF minus EI is given as uh, EF minus EI is given as 0.29 electron volt. So you can write uh, N equals to Ni exponential of minus. This is minus EI minus EF divided by KBT. And this, if you can write as a 10 power 10 exponential of minus 0.29 divided by 0.025, and that you will reach around so this is the exponential term, so this will become positive because EI is less than EF, so this will become positive, and then basically you will reach this will be around uh, 10 power 10 exponential of 0.29 divided by 0.025, so this will become 10 power 10 exponential of 10 approximately, because this is one decimal point shifted. So, the correct option, if you calculate, so this n basically you just calculated by ni exponential of ef minus ei by kt, and that n will be roughly equals to nd, and that this is the same as the uh, same as the doping concentration in the this case this, and they asked about the electron concentration at the interface. So basically, like see, like this EF is conside at the EI level. So basically, at the interface, the semiconductor has become in the intrinsic actually. So just because the semiconductor has become intrinsic, so the carrier concentration will be equal to the intrinsic carrier concentration. So just by visual on also you can answer this question, and this was probably one of the gate question I feel is. So the this if you calculate by n equals to electron concentration in the bulk, so you will reach around 10 power 15 value, and the at the interface this will be equals to the intrinsic carrier concentration. So this is the correct answer will be B1, and other answer will be wrong because intrinsic can't be that large. This is also wrong. This is also wrong. This is also wrong. So now the surface potential. So phi f. Uh, phi f basically you can calculate is basically your it just basically minus of ei minus ef by q. So you can calculate the surface potential is negative because with respect to ef the ei is in negative direction, so surface potential is minus 0.29 electron volt. So basically surface potential is basically in the bulk. So the surface potential in the bulk is this one. So this you can calculate as 0.29, and you can represent it by negative k direction, and that is is basically your the surface potential. That because at the intrinsic level, because at the just at the interface, the surface potential has become zero. The EI minus E have become zero. So the total surface potential has become minus 0.29 electron volt. So this is the correct answer is last one. And the applied gate voltage drop across the oxide region is basically so this so this basically applied gate voltage and drop across the oxide region is so you can calculate basically is your uh, so the uh, uh, surface potential is basically your you can write it you can the surface potential is basically your you can calculate the electric field from this. So basically by calculating area of this you can calculate the surface potential. And basically like the surface potential plus this gate will be equals to the applied gate voltage. So the the surface potential at the uh, so uh, so basically the banding is basically your surface potential inversion, and like the drop across the oxide region you can calculate just by so basically your epsilon in oxide region is basically equals to 3 times epsilon in silicon region. And epsilon in silicon you can calculate by area of the surface potential. So this is half time w depletion width time uh, the surface potential times the phi f, basically because the surface potential is minus phi f. And that basically you can calculate 3 times half of this. And wd you can calculate is qnd by epsilon times so basically you can calculate this by just by the drop across the semiconductor, and that is basically your 0.29 electron volt. And that basically is like the surface potential is equals to q and d by 2 epsilon w square. So w you can calculate is v of silicon multiplied by 2 epsilon by q and d square root actually. So this depletion bit you can calculate. From that you can basically calculate the electric field, and that is basically you can calculate the field in the oxide region. And that and the total voltage, if you calculate the field, and that you can calculate if the field and that the potential drop is just by v across the oxide region is just field in the oxide region times the thickness of the oxide region. So with this, you can calculate the potential drop across the oxide region, and which you will see is around the point minus 49 voltage, because this is in the negative direction, and this is minus 0.49. And that and this to calculate the gate voltage you need to add the v aux plus vsi. Vsi is minus 0.29 plus 0.49. You will see around point minus 0.7. So the correct answer will be this first one, and that is the correct answer. So the depletion width, so basically depletion width as we can calculate here from the field value, you can calculate the depletion width. So basically E of Si is equals to the half of the uh, no, just wait. Yeah, so the surface potential is basically half of the surface potential is basically the area of this curve. So area of this curve, and that is basically E of interface. So this is half of E of Si times W of depletion is the surface potential, and this is given as minus 0.29, and that from this you can calculate uh, the uh, the depletion. So an E of Si you can calculate at the interface. If you put x equals to 0, then basically it will become half of q n d by epsilon w d square, and basically you just from this you can get the depletion width just by the surface potential. So basically it will become so the surface potential Vs will be equals Vsi will be equals to half of uh, half of Qnd by epsilon times Wd square, and Wd you can calculate like 2 epsilon by Qnd times V of Si, and basically square root of this. So if you calculate B of Si is minus, you take mod of that, my 0.29, and that epsilon is given, nd is given, nd we calculated, q is given, and that you can calculate the value of the depletion. So the correct answer you will reach is around 0.586, and that is your the width of the depletion region, and that is in the micrometer region. So that was the last problem from my side. So if you have any doubt in the question we discussed today, you can ask, or we uh, we uh, we we I yeah yeah five okay okay 5 and 4, right? So this one voltage and yeah, so this one, right? Fourth one, right? Okay, so so what will happen is the charge configuration that accurately represents. So this was the band diagram. So see, let me just rub this for a time being. So let me just rub this band diagram here. So let me just explain. So as you can see, let me just discuss for three problem actually. So because this fourth and fifth are extension of third problem. So see like this in the bulk, this EF is closer to the conduction band, and EF is above the EI intrinsic level. So that means if EF is closer to the conduction band, then this is N-type substrate, right? So this is N-type substrate. Okay. So now this we got like what is the bulk substrate actually. So now you see the condition at the interface, what is happening at the interface. So now because of the this applied bias, so the band is moving upward, and this ec is moving upward compared to ef. So if you see at the interface, so basically this e ef minus ec at the interface, so ef minus EC or EC minus EF at the interface is larger than EC minus EF, EC minus EF at bulk. So basically, it is more less N type compared to the bulk actually. So other way you can see it is more P type compared to the bulk. So that means like that like how you create more P type just by removing the some electron out of this region at the interface region. So basically some electrons are pulled out of this region. That why it becoming less N type and more P types, and it is becoming depleted. So we can say this region is depleted of majority charge carriers. So majority charge carriers are pulled away to the substrate, and that's why this is a kind of depletion region. And it can't be the inversion region because this is the surface potential in the bulk, and at the surface potential just this ei and ef is coinciding. For inversion region, this shift in the surface potential should be psi of S is basically 2 times psi F, but this is psi S is just at the psi F. So basically, it's not in the inverted region. So this region is basically the depletion region actually. So now we got what is the MOSFET is biased. So now, because let me draw the band diagram here. So now that band diagram is looking like this. So this is EF, and if you draw this, the oxide, and this is the semiconductor in the bulk EC, and that at the interface is becoming like this. At the interface it's becoming like this. At the interface it's becoming like this, and this is like this. At interface it's becoming like this. So now, as you can see, so now because this region is depleted of charge carrier, so if we draw the charge picture, so basically now since this is the n type, so the charge will be the dopant will be like the dopant will be have the group 5 element which has the ions are positive. So when you take out the electron from this region, the remaining region is uniformly doped ions here. So basically this region will be have ions, and the charge density will be uniformly q n d by epsilon. So this charge density by q n d by epsilon, and that the corresponding opposite charge. So you remove electron from there, from the battery, the electron will get deposited here. So the negative charge equals to this total charge of this will appearing at the interface of the gate region. So this is minus q, and this total charge is plus q. So as per this explanation, the correct answer will be third one. So is that clear, Sanjeev? Okay. So now basically, so to get the electric field, so basically you need to, so this is the charge density. So this is the charge density rho x. Just to get the electric field, you need to integrate the electric field actually. So basically, the in this region actually there are two types of electric field. So in the like so you can apply Gauss law in the different region. So you need to apply this Gauss law in semiconductor region, Gauss law in oxide region. So in the semiconductor region, in the especially in the charge case, so the Gauss law is dE by dx equals to minus q n d by epsilon. So if you integrate this, that you will reach the linear increase in the field values, and you can say, and the at the boundary the field is zero because this region is charge neutral region. There won't be any field through the substrate actually. Especially in the ideal case, we can assume there is a zero field. So if we integrate, then we'll reach out at the minus q n d by epsilon uh, minus x plus wd kind of expression we will get. So at x equals to 0, we will get the field as minus q n d wd by epsilon, and at x equals to w, the field will be 0. So in the so this will be linearly increasing field will be at the interface. So this is the at the so this is ESI. So this is ESI at the interface. Now what will happen? Now if we start to integrate, now because these two, this is oxide region, this is silicon region. So now this is two different like materials are there. So you need to apply the electromagnetic boundary condition here. So basically the that boundary condition is that electrostatic boundary condition. So that is basically D1 minus D2 equals to rho s, because we are assuming ideal Morse capacitor. So the interface trap charge will be 0. So we can write D1 equals to D2. So D1 basically is known as the electric field displacement, and that is equals to epsilon on oxide uh, E ox equals to epsilon of silicon e silicon, and because e silicon at the interface we know, so from that we can calculate the e ox in the oxide region. That will be equals to epsilon of silicon divided by epsilon of ox multiplied by epsilon e of silicon. So that you can, if you put the value, and this field now at the just we got this field. So now we can apply the Gauss law in the oxide region. So basically, the oxide region has rho equals to 0. So we will apply dE by dx equals to 0. And this E will be a constant. And that means at x equals to 0, E equals to this one, whatever this we got at the E oxide interface. And that will be a constant throughout. So the field profile will look like this. So is that clear intuitively? Okay, sir. Yeah. Okay, sir. But oxide region uh, rho equal to 0. Mm-hmm. Mm-hmm. Why, sir? Because actually, so see, like this oxide, basically oxide, like if you consider any dielectric, so basically that can't contain any like finite charges. Like that can have there will be because in the semiconductor we intentionally doped some charges, but the thing is we are considering here as an ideal dielectric actually. So uh, that ideal dielectric, yeah, someone thanks me. Okay, okay, thank you so much for listening also. Yeah, so that basically you are considering an ideal dielectric, like it's an ideal parallel plate capacitor kind of thing. So in parallel plate capacitor also, it exactly the same as parallel plate capacitor actually. So parallel plate capacitor, when you drive in your 12th class base, what you assume is basically here there is no charges. It's free of charge. So then basically you take charge density inside that dielectric to be zero actually. Though no net charge is there. There may be because you are applying some electric field to this dielectric. There may be some bound charges actually. What are the bound charges? So this the uh, like the dielectric has this core atom and outer electron. So when you don't apply the field, then this this outer electron will have perfect like circular or spherical kind of orbit. If you apply the electric field, so there is one concept known as the polarization of atoms actually. So what will happen is this positive and negative charge will get shifted actually. So now the electron cloud will be separated from the nucleus actually. So this will look like this. The plus and minus will get separated. So, but if you consider a microscopic case, this is not the free charges. Actually, this is the microscopic. If you analyze, this is bound charge only. So you will assume that this does not contain any the like that kind of net charges is not there. Total charge inside this. Yeah, 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 yeah. Total charge is neutralized. Yeah. So is that clear to you? Yeah, so in the practical case, what has happened is, so suppose you try deposing like practical devices has like like this oxide has been a like huge challenge actually. So the phenomena of field effect actually discovered in 1920 around. People know that MOSFET will work. What was the problem in that time was people were not able to get that interface properly actually. This has huge charges actually because their material deposition and growth process was not there. Even that this oxide was very bad. So that's why people were not able to get that like experimentally people were not able to test this phenomena of MOSFET. So this became stable like better once people for after the discovery of BJT, people start exploring silicon BJT and those things, and then this thermally grown silicon oxide become popular. and that has very pristine quality actually. So that has very less oxide charges. If your silicon quality is better, then your thermally grown oxide is also at very high quality. So then people then once the people got very good oxide material and that interface, then people start seeing boom in the like MOSFET or like FET kind of technology. So like so that's why after 60s it's become like the other than some power and high front end power application like those NMOS like the BJT logic and those like TTL kind of logic just wipe out from the logic actually. So after that, because the process become so stabilized that it just become completely NMOS or then CMOS and those things. So I hope it is clear actually. Yeah. So you have any other doubt? Okay, so Sarla, you have any other doubt? Okay, fine. So you try solving the this week, maybe practice set and let me know if you have any other doubt next week. So if you don't have any other doubt, then we can end this session and we will meet next time at the same platform with the same time. So thank you so much for patiently listening and have a nice week. And I hope you will enjoy learning this course. Thank you so much. Bye. Have a nice time.